Hello everyone, welcome to my YouTube channel. So we're going to be going over some AICE physics here. It's going to be a practice test which covers units 1 through 8. Don't forget to like and subscribe. Okay, so for number 1A, the table lists some physical quantities and we want to identify with ticks which quantities are vectors and which are scalars. And we have acceleration. In this case, it is a vector, so we're going to be checking the second box. Acceleration is a vector, mainly because scalar is simply just a number, right? And a vector is a number as well as a direction. And acceleration can be, you can be positive or negative. So there is a direction. For example, if we have a box here, we can be accelerating forward or accelerating backwards. Yeah. The difference, or an example of a scalar is kind of like that it can move a certain distance, or sorry, we're going on the displacement. Okay, so for displacement, you can go up or down, so it's going to be a vector. Gravitational potential energy is going to be a scalar because energy does not have a direction, it is simply just a quantity. And then speed as well as temperature are both going to be scalars because they only represent quantities and they don't have a direction associated with them. Yeah, speed and velocity are heavily related, but the only difference between both of these two ideas is that velocity, it has a direction and thus is a vector. All right, for the second one, we are deriving the concept, or we're deriving the kinetic energy of the car. Ignore my remarks before because I'm just saying that, on the actual test that I did, I selected the second box, which led me to lose both of the marks on the question rather than getting both of the marks. So they're really picky about that. So just keep that in mind for future use. Now for BI, we have the formula of a work done on the car, and then we have to show that the kinetic energy of the car is given by the equation. So the formula of work is going to be equal to force times distance. S is the same thing as displacement. As said in the problem, which is just underlined. Yep, so displacement, we're going to have to use a Stewart equation to derive. So in this case, we're going to be using the u plus v over 2 multiplied by t. If I'm not mistaken, that is in the reference sheet. So if you forget a Stewart equation, just remember that there are some formulas in the reference sheet. And in this problem, we are given that the car moves from rest, thus our u is equal to 0. And then we can simplify our equation to vt over 2. And then finally substitute that equation into the original work formula. And then we substitute it in. And then we can further simplify by replacing f with m times a. And then we can use the distributive property. 1/2, not the distributive property, the commutative property. So we could do mv is equal to at. And then it turns out we can simplify this into 1/2 mv squared. This is because v is equal to a plus ut. But this, in this case, u is going to be equal to 0, so it's just at. And thus our equation is E of k is equal to 1/2 mv squared, which is to be shown. All right, the second part, the mass of the car is 920 kilograms. At time t equals 0, the car is at rest. At time t equals 5.8 seconds, its velocity is 17 meters per second. Calculate the kinetic energy of the car at time t equals 5.8 seconds. All right, so we're going to have to use the equation that we just derived before. So we are given the time as well as the velocity and its mass. So if we use the equation, m is going to be equal to 920 kg, and then v is going to be equal to 17 meters per second. And thus E of k is going to be equal to the substitute values in, and then you put in your calculator, and you should get around 132,940. And then we're gonna have to round it to the nearest 2 sig figs. So then we get 130,000 joules, I should say. And now for part 3, we have 2 times, and then we have to calculate the work done against, or the work done against the resistive forces is some value, and then we have to determine the average power output. So the formula for powers in this case is going to be work over time. And in order to calculate the total amount of work, we need to incorporate the work done previously as well as the work done against resistive forces. So we're going to go ahead and add these two up, I believe. So 130,000, and then we add 4.7 thousand, and then you should get 177,000 about, and that is our total work done divided by the time, which is going to be 5.8 minus 0. So it's going to be 5.8 seconds at the bottom, and then you simply just plug that into your calculator, and you should get P is around 31,000 watts. Okay, at time t equals 5.8 seconds, the speed of the car becomes constant. State and explain whether the power of the output of the car is greater than, less than, or same as the output, less than or same as the output power just before t equals 5.8 seconds. So in this case, before the car reaches t equals 5.8 seconds, the output power is less than the output power before 5.8 seconds, because at terminal velocity, the work or the resistive force is going to be constant, which means that before there's less resistive force, and thus less work is going to be done against the resistive force, basically. And there's another way to explain it, as shown. Our next problem, number 2a, state the principle of moments. Alright, so this is a definition problem. The best way to do these problems is just to memorize the definition. Wowie. Who knew this was an AICE Lang class? But in this case, the principle of moments is pretty important because it is describing a lot of like rotational type questions. So the definition is going to be the sum of the clockwise moments is equal to the sum of the anti-clockwise moments or the counterclockwise moments. And another detail that has to be included is that it is within a closed system, meaning that no external force is acting upon the object, and thus the condition before is satisfied, basically. All right, so for the second one, for B, they give us a diagram, which has a person, a beam, a cylinder underwater. And we have to use the given information, and by taking moments about end A, determine the distance x from A to P. All right, so first things first, let's draw arrows of which the directions of the weights are going. So the cylinder has its force going up, and then the weight of gravity of the uniform beam as well as the person are going down. Thus, the sum of the clockwise moments is going to be the beam. I think I do first. Yeah, so it's going to be the beam. It's going to be 1700 newtons, and since it's uniform, the center of gravity is going to be in the middle, so it's going to be the length of the cylinder, or of the entire beam, divided by 2, and then the person, which is going to be 660 newtons multiplied by x meters, and then that is the sum of the clockwise moments. And then now we have the anti-clockwise moments, which is just going to be the cylinder. And they do give information about the cylinder that it is 5 meters away and has a vertical force of 1300 newtons. So it's going to be 1300 multiplied by 5. And then now, due to the principle of moments, we can say that the sum of the clockwise moments is going to be equal to the sum of the anti-clockwise moments. And substituting it in, we get 5100 Newton meters plus 660 Newton meters is going to be equal to 6500 Newton meters. We can go ahead and move solve for x. So 660x is equal to 1400, thus x is equal to 2.1, rounded to 2 sig figs. For the next question, the bottom of the cylinder is submerged in water to depth y as shown in figure 2.2. The beam is still attached to the cylinder but not shown. Force from beam 1300 newtons, blah blah blah. The cylinder has mass 11 kilograms and diameter 0.78 meters. The beam exerts a vertical force of 1300 newtons on the cylinder. The cylinder is in equilibrium. Show that the upward thrust acting on the cylinder is 1400 newtons. All right. So we know that it's submerged and it should have a force of gravity acting down, right? We also have another force acting up, which is going to be the upthrust force from the water. And then we also have the force from the beam, which is 1300 newtons. So the upthrust cancels out with Fg and the force of the beam. And I kind of just substituted in here, but the force of the beam is going to be 1300, and then the FFG is going to be 11 multiplied the gravity constant 9.81, and that should be roughly equal to 1400 newtons. So the water has a density of 990 kilograms per meters cubed. Calculate the depth of y. All right, so you're gonna have to use a formula from your reference sheet. It's simply just the upthrust formula. You can look at it on your reference sheet. Just look through it. It's gonna be on there. Trust me. But the exact formula is going to be U is equal to rho times GV. Where rho is the density, G is the gravity constant, and V is the volume. And we just solved for the upthrust from before, so we can simply substitute in. I think that's what I do here. So it's going to be 1400 is equal to rho, which is given there, 990 multiplied by 9.81 gravity constant, and then V. So the volume that is submerged is the height multiplied by the cross-sectional area. And the cross-sectional area is a circle. So we have to take the radius and we divide by 2, and then we square it and multiply by pi to get the sectional area. And then if we multiply by h, that will be V as shown. I draw another diagram here just to make sure that it's pretty reinforced here and it's more clear. So the radius of that is going to be divided by 2. We have to square and multiply by pi. This is going to be multiplied by y. Yeah. So basically, you solve for h in this case, and you should get that h is equal to 0.30. All right, so for we're given a diagram here, the person can stand anywhere from A to B. On figure 2.3, sketch the variation of the depth of the bottom of the cylinder with the distance from the person from A, where distances 0 and 6. Numerical values are not required. All right, so we have to look at the diagram that we just did and see that our person is standing where we initially have him to stand. And let's say if he moved left, that means that the force that he exerts on a counterclockwise moment, right, it decreases. So x decreases. Thus, the force on the cylinder basically decreases, right? Since the force of the cylinder decreases, we know that the depth of the cylinder will also decrease since there's less upthrust, right? Yeah, so essentially that is the idea. On the contrary, if let's say x increases, the upthrust will also increase, and thus the depth will also increase because of more force. So we can go ahead and draw it. The x and y intercepts will kind of just like, the y-intercept exists because even though the person is on there, if there's no like person on there, there is still a force exerted on the cylinder. So that is just like the minimum amount of depth that the cylinder can uptake, basically. All right, number 3. A steel ball is projected horizontally from the top of the table as shown in figure 2.1. The ball is projected horizontally at a speed of 4.9 meters per second, and the ball lands on the ground, a horizontal distance of 180 centimeters from the edge of the table. Assume that air resistance is negligible. Calculate the time taken for the ball to reach the ground. So we can promptly convert the 180 centimeters into meters, which is going to be 1.8 meters. And we can divide that by the speed of which it travels to get the time. So we could divide by 4.9 meters per second, and then you should get 0.367 seconds. So it's going to be 0.37 when you round it to the when you round it to 2 digits, or 2 cyclics, sorry. The intuition for this problem comes from the formula of d equals st, where s is equal to speed in this case, and d is equal to distance. So distance over speed is going to be equal to time, and that's basically what I just did there. All right, so now let's calculate the vertical component as it hits the ground. So now that we know the Subat equation, v equals u plus at. Initially, our vertical component is non-existent, so u is going to be equal to 0. So v equals at, and then we substitute the values that we know, as shown, and then you should get 3.6 meters per second. All right, now determine the magnitude and the angle to a horizontal of which the velocity of the ball as it hits the ground. So we need to construct our vector, our resultant vector. So in this case, our resultant vector is going to be negative 4.9 multiplied, or not multiplied, but negative 3.6. There's our y component, right? And thus the magnitude is going to be the x component squared, adding the y component squared, and you should get a value of 6.0803, which rounded is going to be 6.1. And now the angle, you can draw a quick diagram if you're unsure. But as shown, we go 4.9 to the left and then down 3.6, and we use the inverse trig function of 3.6 over 4.9. And thus you should get an answer of 36 degrees. All right, so the ball, we're given a steel ball here, and we're given that it's going to be pressing against a spring, and then it's going to be launched outwards. In this case, we have to calculate the density of the steel. So we know that rho is going to be equal to m over v, and they do give us these two values. I low-key forgot to put it within the screenshots. That's low-key my bad. But they do give us the mass and the volume. So in this case, our volume is going to be 4 over 3 pi multiplied by the radius cubed, and our mass is going to be given. But v is going to be equal to 4 over 3 pi multiplied by the radius. This is where I figured it out. That's funny. All right, so the diameter is given 0.016 meters, and our mass is going to be 0.17 kilograms. So we take our diameter, we divide it by 2 to get the radius, and then we cube it. And then we need to find the mass, and the mass is given. So rho is going to be equal to 0.017. And then we divide by the volume that we solve for. And this is going to be equal to 8.0 multiplied by 10 to the third. For II, all the elastic potential energy in the spring is converted into kinetic energy of the ball. Oop. Alright, so I think I forgot to mention one thing, but you can get like a slightly off answer because initially when I did this problem, I only did it that I got 8,000. But I think 7.9 or 8.1 are still acceptable. Anyway, continuing on, the speed of the ball as it leaves the spring is 4.9 meters per second. Show that the minimum elastic potential energy of the spring is 0.2 joules. We have to use the kinetic energy formula, which we solved earlier. But kinetic energy is going to be equal to 1/2 multiplied by 0.017 multiplied by our velocity squared, which is going to be 4.9 seconds. And then we're going to get 0.2 joules, which is going to be the maximum elastic potential energy, simply because the potential energy is going to be converted into kinetic energy. Alright, so I use figure 2.4 to determine the spring constant K of the spring. K is equal to Newton per meter. So in this case, you're going to have to draw a triangle on the graph that they give you because it is based on newtons per centimeter. And in this case, I drew a triangle at the 4 centimeter mark, I believe. At the 4 centimeter mark. And then this translates to about 2.6 on the y-axis. And thus our slope is going to be 2.6 over 4 centimeters. So it's going to be 0.04 meters when you convert it. You should get, in your calculator, K is going to be equal to 65. And that is going to be our answer for that part. Now we have to use our answer in BIII and the value of energy given in BII to determine the compression x of 0 of the spring. So we know that U of P is going to be equal to 1/2 kx squared. This is a formula you might need to memorize. And then we substitute everything that we know. So 0.2 the joules and BII is equal to 1/2 times 65 multiplied by x squared. And then you get x squared. X is going to be 0.078. Alright, for the second one, the steel ball is replaced by a polystyrene ball. I'm pretty sure that's a full foam ball. It has lower mass. Why this ball leaves a spring with a greater speed than that of the steel ball. The mass is lower, and thus the velocity is going to be higher. Simply because the force acting on a ball will be higher, and thus the acceleration is also going to be increased. In this case, I use the kinetic energy explanation where the mass is lower, but there's going to be a higher velocity because the kinetic energy is the same. Why this ball takes a longer time to reach the ball than a steel ball? Well, air resistance provides a force that has a vertical component against the falling ball, basically. Which means, yeah. So it reduces the acceleration as it reaches the ground. All right. So number 4, a small ball is dropped from rest of height above the ground and falls vertically downwards. The ball collides with the ground and bounces back up vertically, reaching a maximum height. The ball has a mass of 0.2 kg and is in contact with the ground for a time of 0.18 seconds. Just before the ball hits the ground, it has speed 5.2 meters per second. And when it leaves the ground, it has velocity 3.6 meters per second. State and explain whether the collision is elastic or inelastic. All right, so first we have to discuss whether or not it is elastic or inelastic. In this case, our collision is going to be inelastic because it is leaving the ground at a different speed, which means that the kinetic energy is not conserved. In an elastic collision, both kinetic energy and momentum are conserved, but in elastic collisions, the kinetic energy is not conserved. Um, and as I just said, speed is not the same, and thus our kinetic energy is also not the same. All right, so for BI, calculate the change in momentum of the ball during the collision with the ground. So we know that momentum is going to be P of F minus P of I. Okay, give me a second. My cat is. All right, so we know that P of F is going to be 0.25 multiplied by 5.2. And our secondary momentum is going to be 0.25, and then it's multiplied by negative 3.6, right? So this is going to be the other direction, right? Because there's one of them's going down, one of them's going up, and you should get a value of 2.2. And then we have II, determine the average force of the ball during the collision with the ground. So the definition of force, which is Newton's second law, is going to be the change in momentum divided by the change in time. The change in momentum we just calculated, which is going to be 2.2, and the change of time is going to be 0.18 seconds. Go ahead and divide this out, and I don't know what I'm yapping about here, but you should get an answer. Of 12 newtons, which is going to be the answer. And now we have to calculate the ratio of H2 divided by H1. So this part is going to probably be a little bit harder than usual because it is a three-mark question, and it will require a little bit of problem solving or more steps involved. So we're gonna have to use Suvat equations in this case to determine the height or the displacement each person gets, right? So it's going to be 9.81 t is equal to 5.2. So that's going to be the H1 part. And the formula that I use is V equals U plus 8t, where U is equal to 0. And then we're just calculating the time it takes for the ball to hit the ground, basically. And it's going to be 0.53 seconds. And then we'll use the displacement formula. S is equal to U plus V over 2 multiplied by T. So it's going to be 5.2 divided by 2 multiplied by 0.53, and then S is going to be equal to 1.37, which is going to be H1. And we do a similar thing for H2. V is going to be equal to U plus AT. Our final velocity is going to be equal to 0, but our initial velocity is going to be equal to 3.6 minus 9.81 multiplied by T. In this case, T is going to be equal to 0.36697. And then we use the same formula, Suvat equation. S is going to be equal to 3.6 divided by 2 multiplied by 0.36697. And then S is going to be equal to 0.666. Yeah, so it's gonna, the first one is gonna be S1, the second one is gonna be S2. And then we go ahead and calculate the ratio. And this is gonna be roughly equal to, I think this is like 0.5 or 48, 0.48. So yeah, that's gonna be the answer for that. Round into two suffix. So yeah. For that question, we use the combination of Suvat equations to determine the heights of which the balls traveled. And then at the end, we just compare the heights. And yeah. And then finally, we have our last question, which is a circuit problem. A cylinder copper wire P of length 0.2 meters is shown. Show that the number density of charge carriers on the wire is 8.3 multiplied by 10 to the 28th. So they do give us information about the current, the resistance, the total number of charge carriers, as well as a cross-sectional area. So to find the number density of charge carriers, you do have to use a formula. I think circuits are like the most formula dense unit. So you're gonna have to know a lot of different formulas for this question, for this unit. So number density is going to be the number of charge carriers, which is big N, and divided by the volume. So in this case, they actually do give us the number of charge carriers N directly, which is 2.6. Yeah, 2.6 multiplied by 10 to the 22. And then now we have to calculate the volume. So they do give us the cross-sectional area as well as the length. So the cross-sectional times the area is going to be equal to the volume. And that is going to be around 8.3. So our number density is going to be 8.3 multiplied by 10 to the 28th. Yeah, so now calculate the average drift speed of the charge carriers electrons in the wire. So one alarm bell that should sound is we're looking for the average drift speed. So speed is simply going to be the distance over time. In this case, I use D as distance. It's just a habit, but in reality, the correct notation should be S over T. But yeah. So we do need to find time as well as distance in order to calculate this speed, right? So we know that the current is going to be the change in Q over the change in time. And they do give us I as well as the change in big Q, I think. Yeah, big Q, which is going to be the number of charge carriers multiplied by the elementary charge. And the elementary charge is given in your formula sheet, the reference sheet, which is going to be 2.6 times 10 to the 22 multiplied by 1.6 times 10 to the negative 19 divided by time. And we only need to divide the numerator of the right side by the current 0.85. And the value that I got is going to be t is going to be equal to, plugging in a calculator, so t is going to be equal to 4.4894 seconds, right? So we have our seconds, and then now we already have our length, which is given, which is going to be 0.24, and we divide by 4.894, and then if you calculate that out, S is going to be equal to 4.9 multiplied by 10 to the negative fifth, which is going to be our answer. So yeah, that's going to be the end of the AICE physics review. So don't forget to like and subscribe. If you have any questions, feel free to comment down below. I'll definitely reply to them. So don't be afraid. No bad questions, right? All right, have a good one.